Yeah, please share the screen whenever you want and we can start.
Okay.
Good. So, hi everyone. It's a pleasure to have the Daniel Brattam from University of Genova today, who will talk us about diffusion in a magnetic field. So as usual, let me say just before, please feel free to ask questions. Keep your mics muted, and just whenever you want to ask a question, unmute yourself and go ahead. Please, Daniel.
Oh, okay. Thank you, Daniel. As you said, today I'm going to talk about diffusion in a magnetic field. Particularly, I'm going to work in 2+1 dimensions, but a lot of the ideas that I discuss will extend to higher dimensions. Here on the side, we've got a little summary of what we're going to discuss today. I'm going to start off by talking about magnetic fields that are order 1 in derivatives. In particular, they vanish in the equilibrium state. So I'll review some old results and the later developments that came from them. And then I'll talk about something very recent that I did with people at Genoa and experimental groups at Dresden and Genoa, which is an actual real material. Then I'll move on to my latest work, which is discussing magnetic fields that are order 0 in derivatives. This is that they are non-zero in the equilibrium state. Before higher sort of hinting at what's coming, hopefully in the not too distant future on the archive. And I'll finish up by talking about sort of a grander idea, what these results from magnetohydrodynamics might suggest about hydrodynamics in holography more than we know at the moment. Okay, good. So with that said, let's get on with it. Let me set the scene a bit. It's a very reasonable question to ask. Why should I care about magnetic fields in 2+1 dimensions? Well, hopefully quite a few are aware, but there are lots of materials that are effectively planar materials. The stereotypical example here is graphene. And the magnetic fields, it's actually relatively easy experimentally to get a constant magnetic field in a flat plane. So that's useful because it's one of the few sort of experimental parameters that's very easy to tune. For example, if another one you might want to change is the doping of different charge carriers in a material, but that's a lot harder. You have to go away, grow a new crystal, maybe the doping is too high, too low, the crystal shatters. With an external magnetic field, it's, in principle, obviously experimentalists will tell you it's a lot harder than this. You can just go and turn the dial on some machine somewhere and it changes the strength of the magnetic field. There's also lots of very interesting effects associated with magnetic fields in 2+1 dimensions. For example, I'm sure everyone here is aware of the Hall effect or suppressing superconductivity. Perhaps people are less aware of anyons. So these are particles that exist in 2+1, basically because of the different nature of the rotation group in that dimension. And they have neither integer nor half integer spin, but some fractional spin. And the way this works is you have some background magnetic field, and if your theory has a Chern-Simons term, magnetic flux gets attached to these charged particles in such a way that when you take one of the particles and move it around the other, you describe the current loop, and the result is that the spin when you go around is not 1, sorry, the change in the sign is not 1 or -1, but some overall phase. Okay, so that's sort of the experimental effects you might be interested in, or at least the system. But also, I mean, I should give my perspective as to why I like magnetic fields in 2+1 dimensions. I think they're theoretically fun, in particular because they don't break spatial rotation invariance, which makes things a lot more difficult normally. And you know, as I said, they have all these bizarre properties. So that's magnetic fields in 2+1. Hopefully I've convinced you, or at least made your mind open enough to think that might be interesting. But what does holography have to do with this? Well, okay, we're in the applied online seminar group here. So There's the standard answer, which is that holography is very useful as a test bed for looking at condensed matter systems, because it's a whole new way of calculating things, and it allows you to calculate things in theories where normally you wouldn't be able to do so. But actually, with respect to magnetic fields, holography has another nice feature. So take, for example, the dionic black hole. In the dionic black hole, using one of these horizon calculations, which I'm sure most of us have done, you can compute the value of the electric, the thermoelectric, and the thermal conductivity to all orders in V. It doesn't matter what the size of V is. It's a relatively straightforward calculation. So in that sense, holography is also, you know, a good place to play with magnetic fields, because you can get exact results relatively easily in a lot of cases. Okay, so that's the scene. Hopefully you see why I'm interested in these things now. So let's now talk about what was done in the past. So we're going to go way back to 2007, when I was just finishing my undergraduate degree. And there are a couple of guys who were interested in a phenomenon in cuprate superconductors, which was the anomalously large Nernst effect. You might recognize these names, they're down here at the bottom. These were the guys. And what they thought might be the case, because the point is that this enormously large Nernst effect is also associated with this phase diagram where you have the strange metal. In particular, whether if you look in the strange metal region, you've got the resistivity going as T. So they put forward this idea that maybe what's behind all these odd effects in the strange metal phase is a quantum critical point hiding under a superconducting dome. I'm sure most of you have seen the diagram. I'll show it in a minute. And that this quantum critical point is controlling all the properties that all the thermodynamic properties and the transport properties that we see. As it's strong coupling, now we know that I'm not sure it was appreciated at the time, but now we definitely know that a strong coupling, one of the best sort of descriptions, one of the descriptions you expect to apply is hydrodynamics. If I'm to give a rough kind of intuitive idea of what that is in terms of a particle picture, your particles are, strongly coupled to each other. They're interacting, very, very strongly, which means that when you make some perturbation of the system, it very quickly spreads out into a region. This is all related to scrambling times and whatnot. So we expect hydrodynamics to be a good description of these strongly coupled systems relatively early on in their evolution when you make some perturbation. So anyway, these guys went away and they wrote down a theory of hydrodynamics to try and describe this quantum critical point. I'm going to give, can I just check, Daniel? You can see the mouse here, right?
Yeah, we can see the mouse, but we were also wondering whether you have a headset or something, because there is a bit of echo.
It might be the fan. Give me one moment. Oh, no, it's the room.
Yeah, that's why I was not interrupting you, because okay.
I don't have a headset, I'm afraid.
Okay, we can understand you, but I
apologize for all.
There's a bit of an echo.
I'll try turning my voice down slightly. If I get too quiet, please say.
Yeah, also don't get too quiet.
I'll try and balance.
It's okay, I think. And we can see your mouse, I think. Move it again.
Yes, here.
Yeah.
Okay, great. So here's one of the constitutive relations. It's for the spatial charge current. And you can see here a sigma naught, an incoherent charge conductivity, and here alpha zero, which is an incoherent thermoelectric conductivity. There's also an expression for the heat current. But it turns out, because of relativistic invariance, that this is not independent of this. In fact, they can all be expressed in terms of the electric conductivity, the incoherent electric conductivity. So, I mean, the authors of this paper made a very big point about the fact, it was a very big point about the fact that everything can be expressed, all the magnetotransport can be expressed in terms of one incoherent quantity that you need to define. So they went away and computed the hydrodynamic correlators, and you find things like the longitudinal charge conductivity and the longitudinal thermal conductivity in the DC is 0. This is the hole conductivity, the electric hole conductivity. It has this expected form. And this is the thermal hole conductivity, and depending on whether you want to subtract the magnetization current or not, you get S over B or S over B minus the magnetization over the temperature. It's just a definition of the heat current. And here we display, I display the correlator that, the correlator that you get from doing that. So the blue dots are actually data for the dynamic black hole. The blue dots are data you get by solving the perturbation equations in the dynamic black hole. This purple dashed line, which is also here, it's just all on top of each other, is the result you get from this paper, these papers, the analytic result. And there's also a red line, which I'll explain in a moment. So this is at relatively low B, and you see the matching is perfect, it's spot on. Okay. But when you turn up B, what you begin to find is that there's a difference between the data, which is again, it's actually dots, but they're very closely spaced. There's blue line here, and this purple dashed line, which is the result from the paper. Now, at the time, what people said was, well, we only expect hydrodynamics to apply when the magnetic field is suitably small with respect to the temperature. So maybe what we're seeing here is the fact that you're considering the magnetic field as much too large. What I'm going to discuss a bit later in this talk, when we get to order 0 magnetic fields, is actually that's not quite correct. And I will show you how to derive this result. This is our result, this red line, which you can see in the hydrodynamic region much better matches the data. Okay. Obviously, outside the hydrodynamic region, it doesn't need to match. And in fact, the nice thing about Hartmann's result is that it goes to the conformal conductivity, but that's not a necessity of the hydrodynamics. Okay, good. So I actually wanted to show you as well that there's another difference that's sort of led us to this study, which is if you look at the thermal conductivity, these conductivities here, they're all fixed by symmetry principles. So if you have a system with that's governed by hydrodynamics, and there's a magnetic field and charged particles, you will find this. Okay. As long as the only effect that's breaking the conservation of spatial momentum is due to the magnetic field. This is exactly what you get for these quantities. However, there is system-dependent information, but all that system-dependent information for the magnetothermal transport is hiding in the thermal conductivities. So what I'm showing here is the difference between the thermal conductivity you can either calculate, which is the blue dots using perturbations in the dynamic black hole, or the red line, which is the analytic results, again from these papers. Oh, sorry. And you can compare that against what you get from the hydrodynamics. And you see that there's a difference, okay? That these two that there's a non-zero difference between what you get from the hydrodynamics for the DC thermal conductivity and what you get from the actual holographic calculation. And again, the authors of these papers make a very sensible solution, suggestion that maybe what's happening is just that the magnetic field is too large. You're outside the magnetohydrodynamic regime. Again, what I'll show is that that's not quite right. And if you include another incoherent conductivity that you didn't think might be there, then you'll be able to match the thermal conductivity to all orders in B. In fact, that's perhaps what you would intuitively expect for hydrodynamics, because you think of, or at least I think of, hydrodynamics as a low frequency regime. And so you would expect it to be able to always get right the DC conductivities. If it doesn't, then maybe something's not quite right. Good. that was 2007. I'm gonna, some other, from this point, there were lots of studies of order 1 magnetic fields. I'm just gonna highlight a few that I had some involvement in or I got interested in. Please don't be insulted if I've not included, your work in here. There's so much to review. So after that paper, people considered the nonlinear fluids. They constructed a gauge gravity, fluid gravity duality between, these fluids with the order 1 magnetic field, the order 1 and derivatives magnetic field, and gravity. They also considered parity violation. That's these guys here. And when you have parity violation, there are extra new transport coefficients that are dissipationless. You also get interesting new effects like Hall viscosity. And actually, that will be one of the questions later on with our study is when you now include this incoherent Hall conductivity, this incoherent charge Hall conductivity, as you'll see, maybe there is now the Hall viscosity as well. But we only looked in the diffusion sector, hence the title of the talk. So I can't give you a yes or no on that at the moment. Also, there have been investigations of magnetic fields in probe-brain models. It's a little less clear here whether people are surreptitiously taking the magnetic field to be order 1 in derivatives or not. You can certainly compute a lot of quantities with an order 0 magnetic field, but when you're matching against hydrodynamics, there's often a hidden assumption somewhere where you take a scaling limit to match the hydrodynamics against the background. And as I mentioned before, these probe-brain models have also been useful for discussing anions, which is something I find quite interesting. And of course, as I've said, there's so many different papers in the literature I can refer to here, but these are all kind of holographic things. What about a real system? Well, my colleagues at Genoa and Dresden actually went about trying to find one. And so we, working with the experimental groups in Genoa and Dresden, I actually have, in the end, I asked them for a little sample, but unfortunately it's in the other room and I don't think I can go and get it reasonably. But I have in a little plastic box a sample of this material. So I feel like a real physicist every time I look at it. So this is the material here. It's a high temperature cuprate superconductor. Now, what Andrea Amoretti, my colleague, he put forward this idea that perhaps one can explain all the features that we see in these high temperature superconductors if we take account in the hydrodynamics of the fact that they also have charge density waves at higher temperatures. So let me explain a little bit about that. So there's lots of experimental evidence for this, that as you increase the temperature, what you find is what is normally a Drude peak in the conductivity starts to become offset from the axis. And when you look at what might be causing that mechanism, I mean, here there are examples where they use X-ray diffraction. They find experimental evidence for these charge density waves. Now, I'm not sure everyone knows what a charge density wave is, so let me give a brief sort of intuitive explanation. This work goes back to 1955, so it's a very old idea. And we'll just look at this little cartoon here. So here we have a one-dimensional model of crystal. So there's fermions and these are the dispersion relations here. So there's fermions, and we will fill up to the Fermi level. Okay. Then what I'm going to say his name wrong, so please forgive me. Piers considered was that if you turn on what happens if you turn on a lattice distortion? So here the lattice spacing is A. Now you turn on a lattice distortion of spacing 2A. So this halves the Brillouin zone from pi over A to pi over 2A. Okay. Why is that an interesting thing? Well, now your Fermi level is at the level of the band gap, this little break here that was initially over here. This is an interesting thing because if you look very closely at the edge of the band gap, you can see it turns down slightly. It's not smooth across this break. So that means that fermions that are sitting right at the band gap experience a decrease in their energy. So if you can balance the decrease in energy from fermions sitting at the Fermi level against the energy required to create the lattice distortion, then maybe the ground state is not one, where the lattice is sitting still, but in fact one where there's no overall distortion. And this is a charge density wave. Okay. So high temperature superconductors. There is evidence for charge density waves. Let's now try and build the charge density wave into a hydrodynamic theory and test it against an actual material, the DC measurements from material, to see whether that is reasonable and it accounts for everything that we see. In particular, this material is the one we'll look at. Why? Well, it has a relatively high critical temperature, relatively low critical temperature, which means you can go quite far down in temperature. Okay. Good. So, what assumptions are we going to make in our hydrodynamic model? We'll do exactly what those papers I talked about from 2007 did. We'll assume there's a relativistic fixed point. We'll turn on a magnetic field that we'll treat as very small. So while it is constant, it's so small compared to other scales in the system, you can effectively take the scaling limit, and that there are no fundamental Hall conductivities. Okay. With that in mind, these are our conservation equations or non-conservation equations. So here we have the charge density and the entropy. Okay. And because we'll work to first order in fluctuations, you can assume the entropy is conserved. The entropy current is conserved. This is the momentum here, and it is not conserved in one part because of the magnetic field, which is here. Another part, we assume coherent mechanisms for the decay of momentum. And then here, this phi I is, represents the charge density wave. Okay. You can combine that phi I into other quantities here. So essentially you just take the curl and the divergence of phi I in the spatial directions. So di phi I and epsilon ij, di phi j. And that gives you lambda 1 and lambda 2. So this is the other hydrodynamic equation. One way to think of it is the analog of a Josephson junction condition, that you have in normal superfluids and superconductors. So that also we allow for some decay rate here, just like we did for the coherent mechanism here. The summary of all that, so those are the non-conservation equations, but the summary of all that is that the hydrodynamics ends up depending in the DC on 4 quantities. The charge density, the entropy, this sigma naught, which we discussed earlier, the incoherent conductivity, and this sigma tilde here. So I think, yeah, we'll define sigma tilde in this way, that the DC conductivity is the sum of this incoherent one and sigma tilde. And sigma tilde turns out to be related to other quantities that appear in these equations. It's not particularly illuminating. But the important point, the point to really make clear here is that there are 4 quantities necessary to specify the DC behavior from the hydrodynamics. Okay, now let's go to experimental data. So this is actually something that Martina got for us. So she went to her laboratory and she did the things that experimentalists do that I can't pretend to understand too deeply. And she came back with the data I'm displaying here. So this is the resistivity, the longitudinal resistivity normalized to its value at 300 Kelvin. And you can see over rather a large range of temperature. that it's approximately linear in the temperature, okay? And these are, the K's and L's here are referring to different crystals that you used. I also haven't displayed it here, but you can show that the resistivity is approximately independent of the magnetic field. So our first piece of data, scaling data, is that the resistivity goes like T and a constant in the magnetic field, okay? Here's another two pictures, again, data that Martina managed to gather. This is the, well, here you can see that there's a T to the 4 - 4 dependence, which we put here. And we have here a B squared dependence, okay? There's also the cotan of the Hall angle. Here you can see that it goes up like 3/2. And again, there's a picture involving the...
Danny, sorry, maybe you said it, but what are the three sets of points, like L2, K10, and K7?
Oh, sorry. Yeah, I think I did say it, but I'll say it again. They're different crystals.
Ah, okay, sorry.
So, I mean, each crystal has slightly different properties. So it's different sizes and whatnot. But yeah, it's different crystals. This is the cotan of the Hall angle, as I was saying. Sorry, I'm just getting back to it. And again, I haven't displayed the picture, but it has this inverse B dependence. And finally, there's this kappa XY, which is the thermal conductivity, the whole thermal conductivity. And you can see it has this T to the -3 dependence from here and a B dependence here. Okay, so that's all very nice. But what does that tell us? Okay, so we have 4 unknown variables from our hydrodynamics, and I've just given you 4 pieces of data. So what you can do is you can fix the scaling of these hydrodynamic variables in terms of data. So now everything is in the hydrodynamics is uniquely fixed. So you might say, well, great, and you haven't learned anything by doing this. But there's actually another measurement Martina made that we can compare to see whether our hydrodynamic theory is predicting the right kind of things. And you can probably tell by the slightly confident smile on my face that it matches. So let's look at that now. This is the Nernst coefficient, the one I mentioned earlier, as the motivation for looking at magnetic fields, the motivation for those 2007 papers. And you can see, using the information we have from before, the Nernst coefficient approximately scales as these quantities. And if you use the hydrodynamics, what it should tell you is that the Nernst coefficient scales as T to the -2.5. Looking at the graph, boom, perfect. So the point is that you actually over-constrain, because we've got data to over-constrain the hydrodynamics. So what should happen generally is if something is over-constrained, then you'll find that you can't match, unless you got the theory right, you can't match your theory quantities to the data. One of them has to be wrong, right? But here, the system's over-constrained and is giving us the right answer. So this suggests that this is a strong suggestion that this might be the right kind of thing. Now, there are some problems with this analysis, in the sense that for it to be completely conclusive, one of the things you should do is look at finite frequency. This is indeed something the experimental groups here in Dresden are doing now, but we'll have to wait for the results of that. I should also say that it's based on an assumption that you might question, because the charge density wave is only known to really appear at higher temperatures. So assuming that it holds down to the quantum critical point is a relatively big assumption. But at least we can say that it's consistent, which is a non-trivial thing. It's consistent even though everything is over-constrained. So that's quite a strong statement. But again, we're going to have to wait until Martina has the finite frequency data before we can say anything conclusively. Good. Right, so now we are moving on to the cases of magnetic fields that are non-zero at equilibrium. And everything we did before when I referred to the holographic answer or even the experimental answer, even if you had a constant magnetic field, what you should be doing at the end is taking some scaling of that magnetic field so that it's small enough that you get the leading answer. But that seems odd. I mean, for the dynamic black hole, we know what the DC thermal conductivity is, and all the DC conductivities to all orders in B. So maybe you might be a bit uncomfortable with that. And that was actually the motivation for going back to the dynamic black hole and looking at it again. So here, one of the things we did was to go away and compute the Lorentz expansion of the charge correlator about the hydrodynamic pole. So I may have to remind some people of that complex analysis you did 4 years ago, 4 to 10 years ago as an undergraduate student. The point is a Lorentz expansion around an isolated pole looks something like the pole plus a constant, plus terms that are omega minus position of pole, plus terms that squared, that cubed, so forth and so on. It's like a generalization of the Taylor expansion. Here, it turns out to be very useful for the dionic black hole to take this, what otherwise looks like a bizarre combination of the pole conductivity, the longitudinal conductivity. The reason for doing this is essentially S-duality invariance in the holographic model, but it also has the nice property of, so in the dionic black hole you have two poles actually in the hydrodynamics. They have different sides of the real part but the same imaginary parts. If you take this combination, you isolate one of those poles. So we went away and we computed numerically the Lorentz expansion around this hydrodynamic pole for the dionic black hole, and the results are shown here. Okay. If you were to take the original 2007 results, what would you find? You would find that this constant term, which I'm calling the incoherent conductivity, I'll explain that in a sec, is purely imaginary, with the sigma naught being a lot less than, less than or equal to 1. So let's have a look over here and see what happens. Indeed, there's an imaginary piece. And for magnetic fields that are low enough, this is increasing magnetic field in this direction, you find that the imaginary part is less than 1. So exactly, you agree in the limits that they discussed with those results. But as you start steadily increasing the magnetic field, different things start to happen. So for low values of the charge density, as you increase the magnetic field, you find that the imaginary part gets bigger than 1. In fact, for arbitrarily small b, it's bigger than 1 as long as your b is bigger than the charge density. But I remind you that in those original papers, they assumed that the charge density was bigger than the magnetic field to derive their result. Perhaps more bizarre is that there's a real part. Going again from here, from the 2007 hydrodynamics, there's no real part. But we found a real part. So there's something that's not quite right here. The hydrodynamics is not quite describing what you're finding from the dionic black hole. In fact, if you trace this backwards in these correlators, what you'll see is that you need a constant term you need an incoherent Hall conductivity to appear in this piece to explain these results. So you don't see it here because I've plotted against the charge density, but all of these are linear in B, which I'm stating here. And the red lines will be the results I derive later. So you can see they're a pretty good match. I'm just giving you a heads up. But the point is that the original papers seem to be missing an incoherent Hall conductivity. And we're going to go ahead and try and explain that now. Before I move on, let me make one more point here, which is about my use of the term incoherent conductivity. So there's been a fair bit of research in the literature, about these quantities. The idea is that when you start including coherent mechanisms for, say, the momentum loss, then there is a part of your conductivity that really only depends on, that is independent of those coherent mechanisms. And that's an intuitive kind of idea. It was formalized in several papers by Davison and Goutureau and others. In the case when there is no magnetic field, because you can talk about the part of the charge current that is not carried along by momentum. Unfortunately, when there's a magnetic field, this doesn't work anymore because they start turning into each other. So you have to come up with a slightly different definition of incoherent conductivity. So when I refer to incoherent conductivity in the case of a magnetic field, I'm going to refer to this constant term in the Lorentz expansion. Why do I do that? Well, what does adding coherent effects look like? It looks like replacing the frequency by the frequency minus I gamma, where this accounts for the dissipation effects. So the bit of the Lorentz expansion that's going to be independent of that is exactly this constant term. Okay, so that is an intuitive, I wouldn't say very precise, but an intuitive idea of what it means to be an incoherent conductivity with a magnetic field. And of course, you're free to completely disagree with that definition. It's mine, so you can disagree as you please.
Can I ask
yes.
a question? Yeah.
Sorry.
Carl. Hi.
Hi, Carl.
Let me see. So what determines what is gamma, your capital gamma?
Well, for example, momentum dissipation. I try to just, it's not meant to be precise.
Yeah, I understand it, but it seems to me now, if I, okay.
I'm not trying to be precise.
Let me ask the other way around.
Mm-hmm.
How do you define omega hydro? You see, because you have a pole, the pole has a real part and an imaginary part.
Yes.
And you seem to have some method to, out of this imaginary part, you are able somehow to single out the gamma. Why the gamma is not part of the hydro? And how do you make this unique, this division? There must be some, you have this imaginary part in some way, you have to divide up in a gamma and the stuff which is not gamma.
Well, okay, so I have a more precise answer and a slightly less precise answer. So let me do the slightly less precise answer first. What I had in my head when I wrote this down was that you have some hydrodynamic model, and initially there's no gamma ij pj, and then you turn it on. And when I say omega hydro here, I'm just referring to the bit with gamma equal to 0. But you are right.
Yeah.
In fact, the hydro mode, when you turn on these coherent mechanisms, is exactly includes this gamma term. Yeah. So maybe this is a bad labeling.
Okay.
But that's what I had in mind.
You know, what you said is, of course, right. It works, but somehow it assumes that gamma is very small, right? That
yes.
Is, yeah.
Absolutely.
Okay.
And I have comments about that later, but one of the things that will be the upshot of this study is that you can consider magnetic fields that were larger than you thought because they're not derivative anymore, they're order 0, so they're in the background. And I have a question now about whether other terms that occur in, I think it's a universal name here, but in quasi-hydrodynamics, hydrodynamics with these broken charges, whether these terms can be also non-zero in the background generally. That's actually something I really want to investigate because I think that's a very nice idea, but I don't know. So here implicitly you're right, I'm assuming gamma is small.
Okay, thanks.
No worries. Thank you. Okay, so my point was that something's amiss. We need to explain it. Okay, and I define the coherent conductivity. Great. Good. So let's go back to some of the things that were done in that 2007 paper and learn some things. So one of the results from that paper concerns the ward identities and the relation between different two-point functions. So I give one example of them here. So this is the charge current correlator, and this is the charge current heat current correlator. So if you think about it for a minute, this implies something about the small omega expansion of these quantities. Oh, as long as B is taken to be order 0 in derivatives. Okay. In particular, it tells you that terms from here appear at one higher order in omega as terms in here. I hope that's clear. So there's a crossing of the Taylor series of these two objects between different values, different orders of omega. And it turns out that if you look at Hartnell actually made this point, so I'll just repeat it, that everything can be expressed in terms of the AC electric conductivity. So the thermoelectric and the thermal conductivities, the ACs, can be completely expressed in terms of the electric conductivity, the AC electric conductivity. In particular, at small omega, which I'm going to show I have here, it begins as rho over B. That was the result we had before. This here is the thermoelectric piece. Again, it's just really fixed by thermodynamics. And then at order omega squared, you find that the model dependent information starts appearing. So that's this thermal Hall conductivity at zero frequency, and this longitudinal thermal conductivity at 0 frequency. And I've sort of plotted them here for an example B. Okay. So the takeaway from this is that magnetothermal transport information is in the charge conductivity up to order omega squared and small omega. Now, I think, I don't want to put words in their mouths, but I think when they initially were looking at this, because they were thinking of B as small, and in particular omega B going like omega, they stopped at this point here. So they made sure everything matched up to order omega. But what we're going to do is ensure it matches up to order omega squared because of the, there is information here, magneto transport information here. Okay, great. So let's go away and now do some hydrodynamics. This here is the conservation of momentum, spatial momentum. It's just given in terms of the usual thing, the electromagnetic field strength acting on the charge currents. Here, this is the electric field. Oh, I've got two deltas. I'll remove one of them when I send it to you again, Daniel. And this is the spatial current. And so that's one of your equations. And the other equation you have here is the constitutive relation for the charge currents. So this IJ is a tensor structure, okay? But we all know because rotation invariance is conserved in the background, you can break this apart into two pieces. A delta IJ piece, but also because I'm not going to make any assumptions about whether B is, what the size of B is, you can also break it into a piece that's proportional to Fij. Okay. If you go away and do that and compute the correlators, you'll find that the charge conductivity as this generic form. Obviously, it looks more complicated. Alpha 1, alpha 2, and alpha 3 are just, variables in terms of, the things we had across the page, kappa H and the entropy and the temperature, the charge density. So our correlator has this general form, and we know what the expansion of this quantity is at small omega. It's this. So what one can do is match the small omega expansion from the Ward identity against the small omega expansion of the correlator and extract the transport coefficients. In particular, this is going to, because you have three pieces of data here, the leading term at omega equals 0, the next to leading order term omega to power of 1 and the omega squared, you're going to be able to fix all three of these quantities. So everything in your hydrodynamic correlator is completely fixed by the DC. There is no room for anything else. It's all done. And whatever you get, that's the answer. Although I should mention, I've been having a long discussion with Ben Withers about this. But let's not, in essence, whether you can have omega dependent corrections to these, I'm not sure yet. But let's for now take what I just said, that this is everything you can have in hydrodynamics. Once you do that, you can plot the charge conductivity. This is the real part of the longitudinal charge conductivity, and voila, you have a much better fit. So this was the results from the 2007 paper, and you see it vastly underestimates the value of the charge conductivity. The red line is much, much better. I accept that as the frequency gets large, it doesn't tend to the conformal value, but there's no reason to expect that at all from the hydrodynamic correlator. It was just very lucky that it did so for this 2007 result. So in this, someone speaking?
Yeah, it's Blaise. Hi.
Hi, Blaise.
May I ask a question about the fit?
Yes.
Because if I stare at this plot, it looks like your blue line, your data, it's going above the red line and then back down below.
Yes. Yeah, this is.
So the match really is like until, let's say, 0.05.
Yeah, but, well, I mean, there's numerical error.
Not really 0.02 and 0.2.
Yeah, okay. I mean, I agree. I picked a particularly large value of the magnetic field here, which looked like it kind of matched. But you're right, it slightly underestimates.
The point with Ig omega is that is approaching the conformal value again, which is 1 instead of hydro, which is sigma inc.
Yeah.
So actually the less you get, the smaller you get B, the smaller sigma inc is, and then the better the agreement is.
Yeah, you just hit exactly what I'm about to show to you guys.
And so before you do that, so should I, because your whole incoherent conductivity, this is something that's order B.
Yes.
And it multiplies something that has one derivative in the hydrodynamic constitutive relations. So should I think of it as including a transport coefficient from second order magnetohydrodynamics? And if so, how do you know that there are not other second order hydro transport coefficients that will also enter into the AC conductivities?
So good. The answer to that question is, I would say, is no, you shouldn't think of it as a second order term. It's a first order term. The magnetic field is a constant. It's not order 1 in derivatives. It's order 0 in derivatives. That's the way I'm treating it. And so that's also part of why it was missed, because in, say, the parity violating work, for example, they consider order 1 magnetic fields. then you're right. It's lower down in the derivative expansion. And then you would worry that other terms should also be included in the result. And in fact, that's something that I find very interesting, and it was something I was going to mention later, but I'll mention it now. I'm not sure what the relationship is between this result where you treat the magnetic field as a constant, and if you say expand in small magnetic fields, whether the terms you get from that small magnetic field expansion do map onto exactly the terms you get from treating the magnetic field as order 1 in derivatives. Yeah, so I mean, it's a good question. I honestly don't know the answer, but here I would insist that one thinks of the magnetic field as order 0 in derivatives, because it's in the background, it's part of the background of the problem. And in the past, what happened was people took a scaling limit to match the two. And I've not had to do that. I just assumed it was a constant here, and I got better results. Does that answer your question, Blaise? I'm not entirely...
Well, I guess what I'm asking is take the weak field magnetohydro that was written back then, and then classify all second order corrections that enter into linear hydro.
Yes.
Then for sure, this sigma whole inc would be one of these terms. And my question is whether there would be others. And have you exhausted all the possible set of corrections that could enter? And I guess an additional question that's related to your treating B in the background is what if you had just used the expressions from weak field magnetohydro, but evaluated all thermodynamic quantities at non-zero B, which we know how to do using the Rice-Nordstrom black hole. So how much of these corrections should I think of as corrections to the static susceptibilities that enter into hydrodynamics? Instead of having n at b equals 0, you take n at non-zero b. And would that improve the fit?
It improves the fit slightly. I did do this. Yeah, I know what you're asking. I did do this. It improves the fit slightly, but nowhere near as much as including an incoherent hole conductivity. The matching, I mean, the difference between the 2007 results where you don't include B in these static susceptibilities is not that great. It's a very small difference to the way the magnetic field appears.
Also, the thermal conductivities are not matching at all, even if you modify the susceptibilities.
Mm-hmm. Yeah, I'm sorry I didn't understand the question first. But yes, that's what I would say. That I checked, there wasn't that much improvement. You need the incoherent hole conductivity.
Okay, thanks.
No worries. Yes, so good. So yeah, I would say that I've classified everything you can possibly have because I've set the spatial momentum to 0. I've assumed that you only have a single pole, so there's no order omega corrections to here, and then all the constants that appear here, I'm not assuming anything about B. So I would suggest you have everything you could possibly have here. Yeah. Okay, good. So as Andrea was pointing out, there's this point about matching the incoherent conductivity, what the hydrodynamic correlator does at large frequencies. So there's this intuitive idea that I didn't actually know about, Andrea explained to me, is that if you look at the charge correlator at relatively large frequencies, what you will see in that charge correlator is a feature. And this feature tends to sit where the incoherent, tends to sit, its value is at the where you get the incoherent conductivity. It's at the same value as the incoherent conductivity. So let me give an example to explain more carefully what I'm saying here. So this is a case where the magnetic field is a lot less than charge density. Here is the plot of the longitudinal conductivity as a function of omega. And again, you can probably see the blue dots on the purple line, everything matches very nicely. If you zoom in about here, what you find is this shape here. So there's actually a minimum prior to the conductivity taking the conformal value of 1. Okay? And that minimum sits exactly at the value, almost, I mean, up to numerical error obviously, sits at the value of the incoherent conductivity. Okay? So that's n a lot greater than b. This is n a lot smaller than b. You find that the feature now becomes a maximum rather than a minimum. Okay, and again here we have the conductivity as a function of omega. I've chosen these values very small so that the Hartnell result and our result match each other nicely. And here something happens when b is approximately equal to n, but there's no clear maximum or minimum. I'm going to summarize these in a sec. I'm sorry if this is confusing them. So let me summarize them to make it a bit easier. Okay. So this is the charge density here. This is where the charge density is equal to the magnetic field. I pick some value of the magnetic field. So this is the flow of that minimum. So very low charge densities, that minimum tends to 1. And it stays mostly at 1 as you increase the charge density until you get to the point where rho is approximately equal to b. Okay. Here, rho is greater than b, and this result is our result of the incoherent conductivity. Here is the result from the 2007 paper. So you can see it's quite an underestimation of the value of the incoherent conductivity and simultaneously the position of this feature. So that's the flow of the minimum as a function of the charge density. Here you can also see the maximum. Okay. So these blue dots are the flow of the maximum, and the red line is once again our expression for the incoherent charge conductivity. And you see it's an excellent match. Eventually, when the magnetic field gets too large, obviously it doesn't match. But for moderately big magnetic fields, it does match. In fact, it matches much better than the 2007 result, where the incoherent longitudinal conductivity is bounded above always by 1. Here, you explain this fact that, sorry, that's a point I should have made earlier, that the 2007 result, the longitudinal conductivity is always bounded above by 1. But if you look at the data, sometimes it's bigger than 1. And our result matches on exactly to that value. So I would take this as very good evidence, you know, very good supporting evidence for the existence of this incoherent Hall conductivity. I'm sorry I'm not giving the expressions, but there's a reason for doing that. They're kind of long and ugly and very unilluminating, but you can go to the paper. They're available there if you really want to look at them. There is something.
May I interrupt again?
Of course, please.
If you go back a couple, so this feature, so go back again. Yeah, this feature, this maximum or minimum. So you say that it's approximately sitting at sigma 0.
Yes.
Right. So that gives you some kind of estimate for the scale omega over alpha, where you might expect your hydrodynamic description to hold.
Perfectly, yes, absolutely.
How does this compare to the previous plot that you were showing us, the one that we were just discussing just a bit before? Yeah, that one. Where is that scale sitting for these particular values on this particular plot?
Okay, so this plot here, yeah, is
So is it all the way to the maximum or before?
Yeah, I would say the magnetic field here is a bit too hard to see it. It's in a slightly lower magnetic field. There's more of an overlap between the red line and the blue. So yeah, I would suggest that I pick the magnetic field too large here. Sorry about that. But yeah, so let me show you here. I mean, these are essentially the same plots as this, only in a logarithmic scale instead. And I mean, the feature we're talking about is here, and in this case, and here in this case, hidden under everything. But I picked the magnetic field low enough such that, you know, this is a good match. There's still a difference between the two.
Mm-hmm.
But it's a good match at this point, a better match than 1, which is what you get from the old result. Yeah. Is that sort of answered what you're asking, Blaise? Or?
Yeah.
Okay, great. So yeah, I'm glad you asked that, Blaise, because I was about to get on to a point that still really kind of bothers me about this whole thing, which is to do with the quasi-normal modes. Now, there's a lot of work in the literature very recently where they're looking at this resummation approach. This is essentially what one does is, I'll go with what Withers does here, is you linearize the hydrodynamic equations, you match the transport coefficients against the flow of the hydrodynamic pole, which is the pole that's closest to the origin. And then by looking at how those coefficients grow, you can say where the hydrodynamic series converges. And in fact, what you find is that this hydrodynamic series tends to not converge when I'm doing it here at finite k, when the diffusive pole hits a non-hydrodynamic pole. Okay, and there's lots of really sort of interesting studies about this. But the point I want to make is the following: in principle, I fixed everything that one could have in hydrodynamics. And still, if you look at the quasi-normal mode, what you're finding is that there's a difference between the numerical quasi-normal mode and the result I calculate. This is the real part over here, and this is the imaginary part. Now, I want to understand why that is. So one thing you might be tempted to say, this is one avenue I want to think about, is that you can ask how you fix transport coefficients in hydrodynamics. And I chose to fix the DC conductivities. I said, whatever happens, we have to get the DC conductivities right for all values of P. What you could have done instead is said, okay, I'm happy to get those DC conductivities a little bit wrong, as long as I always get the hydrodynamic pole correct for all orders of B, up until I presume the point where it collides with another pole. And I at the moment, I can't tell you, and I think this is an interesting question, as to what's the best way to do this. It might be the case that even that's the wrong way to think about this. Maybe what magnetohydrodynamics is doing here is telling you, actually, I still can't, even with this incoherent pole conductivity, you still can't have arbitrarily large magnetic fields. You can only match to magnetic fields in up to some order. And that way, I think you should be able to get more of the quasi-normal mode and, you know, the DC conductivities up to some order in B. But it's very, very unclear to me what the final answer is. And that's actually one of the reasons I want to start looking more into these resummation approaches that people are talking about. Because maybe it becomes clear when you're, say, one thing you could do is try and analytically continue the dionic black hole to you know, complex magnetic fields and look for poles in that flame. And then you might see that the hydrodynamic series is only convergent in some region. And one shouldn't trust, you know, the results to arbitrary B. But honestly, at the moment, I don't know the answer. But I think it's a very interesting thing to look at. Yeah. Okay. And let me give you a heads up about some future results that will be coming out from the group at Genoa. And obviously, Daniel's smiling because he's been working on these too. So here's a couple of plots. What we're interested in is going back to the charge density wave case with magnetic fields and seeing what happens if you treat the magnetic field now as truly a constant in the background, the same way that we did with the dionic black hole. What I've shown here is that there are some features to explain in the correlators that we've got so far. Actually, this blue line, this blue line here is the result you get from treating V as order 1 in derivatives, if I remember correctly. But you all, regardless of what order you treat V, you often find that the charge conductivity looks right, but you won't be able to match the thermal conductivity. So looking at the charge density is not necessarily the best way to tell if there's a difference. But the features we have to explain from the hydrodynamics, these are spontaneous breakings of translation invariance. So you have some scalar that takes some background values spontaneously, is that there are two poles. That's very different to what we had in the dionic case. In essence, going back to the thing that Carl was talking about, because there's a mixing between gamma, the decay from gamma, and B. And so you end up with two poles with different amounts of these effects. And I'd like to understand, hopefully we'll be able to say in the not too distant future, how to extract the different effects from these poles. In particular, can everything once again be determined in terms of DC data? That's not clear to me. It's a question I would like the answer to. But keep your eye on the archive. Hopefully in the not too distant future, although it's taken a very long time so far, we'll be able to give you an answer to that one. Okay. Finally, I would like to...
May I ask a question about your question? So the DC conductivity, so let's say I consider the full charge current correlator.
Yes.
This is written as a collection of poles.
Yes.
Plus some analytic pieces.
Yes.
And if I take the zero frequency limit, the residues, all of these poles are going to contribute, plus the analytical pieces.
Yes.
And so the DC conductivity is a very complicated sum of all of these different contributions that come from many things. And on the other hand, hydrodynamics is a theory of, well, at least normally only gapless poles, but you may try to augment it by including some gap pole that sit parametrically closer to the real axis than all other poles. So I would say by assumption, you're going to miss some of these contributions. And you're just hoping that you're working in a regime, or you're making sure that you're working in a regime where you can neglect them. So when you say that you want to determine everything in terms of DC data, aren't you like putting things into the hydrodynamics that you shouldn't? Because somehow you're bringing back all information from all of these UV poles into your infrared theory without augmenting it with those poles. And I have trouble seeing how this is well defined.
Okay. So yes, I think that's a perfectly justified thing to worry about. But so we hopefully agree that if you take B small enough, such that the hydrodynamic pole is close to the origin, then you can essentially, that the rest of the information from the other poles is sort of damped out. Do we agree on this, or do we disagree?
Well, I would say in some cases I would agree, in others not necessarily. It kind of depends on what the spectrum of poles is.
Right, okay. But Sure.
But it's true that if the cyclotron pole that comes from turning on a non-zero B is distant enough from all of the other poles that sit at, say, other temperature, then yeah, sure, that would be a good thing to do.
So I would ask one to define distant enough. Therein lies the problem. It seems like with the ionic black hole, distant enough was bigger than you might have thought it would be. Again, that's a statement based on qualitative matching of things, I would say.
I don't. My problem isn't really with that statement, because I think you can always augment the range where the hydrodynamic theory you're writing down is matching to whatever correlator you're looking at by including more terms in the hydrodynamic expansion.
Yeah.
So you'll improve your match by doing that.
Mm-hmm.
However, you seem to be doing something different, because now you're matching the DC data, and the DC data knows about everything.
Yes.
All of the expectations, because these formulae we have from holography, they're non-perturbative, they're just exact.
Yes.
So I would not expect them to hold if I'm trying to compare to hydrodynamics, at least not exactly, especially if I'm breaking a hydrodynamics, strictly speaking, by including gap pole into the hydro.
I mean, I feel that issue. I would say that normally in hydrodynamics, you do match the DC values of things. And if you don't match the DC values of things, you worry. You're right that I'm going in the opposite direction. I'm using the DC to fix the hydrodynamic correlator. Whereas normally what you do is you get the hydrodynamic correlator and you see that it matches the DC. And if it doesn't match the DC, you have questions.
At least for simple momentum relaxation, we know that this is not right.
Yes.
That it wasn't working out like that. You were not matching the hydro. You need to be more careful and include higher order corrections. But now, it could be that the case of magnetic field is a bit special, and you can get away with matching DC conductivities. But I don't see how this is going to be true of any type of generic quasi-hydrodynamic theory. I think magnetic field breaks things in a very specific way.
I think the answer is yes, in the sense in the spontaneous case with no momentum relaxation, you can, I guess, but as soon as you switch on momentum relaxation, you cannot express everything in terms of DC data for sure.
But here you have two peaks, so you have momentum relaxation, no?
Yeah, I think the figure here is not is a little bit misleading. So in order to, the point is that when you have no momentum relaxation, you can express like gamma 1 and gamma 1 all and all this translocation in terms of DC data. But as soon as you get momentum relaxation, you have this capital omega that you always get that you will be never able to determine in terms of DC data. So you need the poles, and then you are just getting the lowest poles. And in some sense, you're assuming that hydro holds because you're just taking the two lowest poles.
But wait, so these two poles, we agree that these are the magnetoplasmon and the pinned magnetophonon.
Yep.
Okay.
Yeah.
So these are still hydrodynamic excitations that previously were not gapped and that now are gapped.
Yeah.
In contrast to all of the other poles that are sitting further lower in the lower half plane, and which in principle might also contribute to the DC conductivity. But if they sit sufficiently far down, then this contribution is negligible.
Yes.
Yes, I think they sit. I mean, at least in our regime, they sit really far down. That's true,
yeah, for
sure. So,
yeah. So as long as you do that, then you're fine.
Yeah.
But this is not going to be true generally.
No, I think.
I mean, that might be exactly what's behind the non-matching, the quasi-normal modes I was talking about. I mean, yeah, generally fine, but I have hopes that in specific situations that you will be able to match things using DC data for other quasi-hydrodynamic systems.
Another way of phrasing this is that say that you take B now in this system, you take B to be extremely large.
Yes.
Then your cyclotron pole is shooting off to -infinity and will essentially cease to contribute to the DC conductivity. And you'll find that you can approximate the non-perturbative DC conductivity just by looking at the residue of the first peak.
Yeah. Yeah, I think so. I think you're right. It's just
that's just because that pole has, gone to the UV, essentially.
Good point. Okay, I'm gonna have to think some more about it. Thank you, please.
Maybe Danny, try to. I mean, it's 20 minutes.
I mean, I'm coming to my last slide.
Okay,
so.
Maybe try to conclude.
Okay. Sorry, I didn't realize we'd gone over time. I apologize.
No, there was plenty of questions. I was just like, it would be nice to get some conclusion.
Yeah, so the conclusion is that the small conclusion is that one should maybe include a whole conductivity, an incoherent whole conductivity proportional to B in one's hydrodynamics if you want to match things properly. So now there's lots of fun to be had. For example, you can go away to probe brains, which is very easy to get the correlator again, and you can do this exact Lorentz expansion and determine whether there's a piece that goes like B, or whether there's an incoherent whole conductivity. And that perhaps hydrodynamics with this magnetic field is well defined in regimes of B you otherwise thought it wasn't. So that's the small takeaway. The big takeaway is maybe quasi-hydrodynamics is defined in regions that you didn't expect it to be well defined, but you get better approximations than you would otherwise have expected. On this, I mean, we just had a talk about momentum dissipation, but there's also things like probe brains or anion systems. All these things are quasi-hydrodynamic systems. And the question is, if you treat the parameter responsible for breaking your symmetry, so for example, that was B in the case of momentum dissipation in the dynamic black hole, it broke conservation of spatial momentum. If you treat it truly as something that is non-zero in the background, so you're not doing the scaling limit, which was essentially behind everything that was done before, do you get a well-defined hydrodynamics? Does it match the correlators that you get from holography better than you otherwise would have assumed? And that's a question I think is really sort of like a research program that's really worth looking into in the near future. Now, with that said, thank you very much. Sorry, I went over time.
Don't be sorry at all. There was plenty of questions. Thanks a lot, Danny. And please, people, feel free to ask questions and make comments.
Can I comment about like the word magnetohydrodynamics? Maybe I should wait until the recording is off. But so I mean in the so I think in the normal magnet, I mean there is like a word that say magnetotransport and magnetohydrodynamic, and I think MHD in the typical sense, like that's the one that plasma people use. This is the one where magnetic field is actually dynamical.
I'm sorry if I misled you into this talk.
No. I mean, I already seen it in the paper, but like I was confused, like whether it's a magnetic field dynamical here, or is it just the magnetotransport?
No,
like where you probe it, where basically you force the fluid with a strong magnetic field. Yes,
exactly. I mean, that's also the situation that you find in a lot of condensed matter experiments, right? You have an external magnetic field. But I agree the terminology is not particularly good. Do you have a better one you might suggest?
I think magnetotransport is what people used before, but
okay.
And I think that there's magnetohydrodynamic kick in some papers, but But then it's get confusing whether is this the one that plasma people use or is it the one that that John and Cole use.
Well, I'll see if I can get Daniel to change my abstract to reflect that. Sorry, Daniel.
And also can I comment about the probe brain case?
Mm-hmm.
So there is a paper by I think by Andy Lucas and I think Chen Lin.
I know exactly which paper. Yes.
Okay. Yeah. So okay, I mean I have nothing to add if you know about that already.
I do know about that paper, but yeah, I think they work at zero magnetic field. I don't remember now. But that's exactly one of the systems I wanted to look at to do exactly the same analysis, essentially, one does for the Dionet black hole, because probe brains are particularly nice when it comes to computing things with magnetic fields. And so one can then look at this probe brain model. And I even gave away the diagnostic you can use, which is to take the correlator, do a numerical Lorentz expansion, which there's, I forgot to mention that there's a really good macro in Mathematica called n-residue, which does this for you. You just got to make sure you got your numerical pole right. So use n-residue to compute the Lorentz expansion around this pole. And you look at the constant term and you ask, is there a real part? If there's a real part as proportional to p, you probably have incoherent hole conductivity. So yeah, I think that's worth looking at.
So when you're talking about the probe, making comments about the probe brains, is it because you want to consider the momentum non-conservation of probe brains as similar to a constant magnetic field, or what is it?
No, I want to genuinely turn on a magnetic field in those cases. But
okay, because probe brains already have this strange.
Yes.
Okay.
Yeah, exactly. And actually, there's just to plug one of my older papers in this regard. I've got papers in the past on looking at anyons from the probe brain models, and you can use. Hello?
Sorry?
Oh, sorry. I thought someone was talking.
No. Oh, at least not.
And you can use SL2Z dualities to take the normal probe brain model and produce a model of anyons. And there you can find that you can move the peak by dialing the Chern-Simons parameter. But while you can control where the peak is positioned, it's still not clear to me how this is related to momentum dissipation, which is one of the sort of the things that people are interested in for the probe brains, because you're exactly right that they have already inherent in them some kind of dissipation. Whether it's momentum dissipation is also not clear, because you sort of separated the degrees of freedom of the probe brain from the background. That's where the momentum perturbations would be. There's a lot that I think is still not clear in that scenario, but it's totally worth looking at. And as I said, there's a very simple diagnostic to determine whether there's an incoherent hole conductivity or not.
More questions or comments? Nick is still unmuted, but I don't think.
I'm not sure, but I'm thinking whether I should ask this or should I wait until the session is over. Maybe you could ask it now. So if you have
if you want me to stop the recording.
Well, okay, fine. No. Okay, I just wonder, like, if you have a incoherent hole conductivity, like, so are you assuming that there would be like additional almost conserved currents? And I mean, do you have like you thought about like what would it mean?
Why additional?
Yeah.
Okay, I'm not sure I misunderstood the point, but like it like the fact that there is additional peak.
I would say like simply, if you have Ji and you assume that, forget about momentum, assume that momentum isn't conserved and that momentum decays quickly, then and you could build your hydrodynamics with gradients of, say, chemical potential, and you had a B field that violates parity, then you would naturally write some matrix that, like, Ji is sigma ij grad J mu, right?
Mm-hmm.
So this is your incoherent, your conductivity matrix sigma hat would have a diagonal part and an off-diagonal part. And that has nothing to do with extra conserved currents or anything like that. It's just that you're breaking parity, and so this term is allowed. And my comment earlier in the talk was that even in the weak field magnetohydro or magnetotransport, however you want to call it, that term would precisely show up at second order in derivatives, because that's one of the terms that you're allowed to write.
Absolutely.
It's just that in the mind of the 2007 people, this is second order in derivatives.
Yeah, I agree.
So they didn't write it, and probably didn't realize at the time that this was important to get a good match to the thermal conductivities, etc.
Yeah, I mean, I had exactly this conversation with Pavel because he asked me how it was different to his parity violating case. And in the parity violating case, in the holographic model, you have these Chern-Simons terms. So you have a fundamental breaking of parity invariance. Here, your microscopic theory doesn't break parity invariance. It's only as a consequence of the magnetic field that parity invariance is broken. And that would be in their model exactly order d squared, partial squared, exactly as Blaise says.
I see, thank you.
Any more questions, comments? Okay, we've had plenty. So. Okay, good. So thanks everyone. And as usual, I will just leave this open in case people wants to keep discussing, which I was happy to see that sometimes it has happened. So I will stop the recording now. But let me just say that in a week we have a colloquium by Paul Romatzke. So